This is the ELEC 1510 Logic Design Lecture 1 Video 3, an Introduction to Logic, which corresponds to the textbooks section 1.9. Okay, so let's discuss what a binary variable is. We already know that binary numbers can have the values 0 or 1. So bits can be either 0 or 1, on or off. Binary variables are variables like you would normally use in algebra, like the letter x here. X, say, can be a variable whose value is either 0 or 1. So it takes one of those binary values, 0 or 1. Z, perhaps, can also be a variable. Basically, any letter or symbol or anything you want can be a variable, just like in algebra. We can have equations with variables in them. So, for example, z is equal to x. That means that if x is 0, z is 0, and if x is 1, z is 1. That seems straightforward, but this is going to get very complicated very quickly. Let's wonder, can you just do anything to these sort of binary equations that you want? Can you have z equal to 2x? No, you can't. These equations don't work the same as normal algebraic equations. This is going to be called Boolean algebra, which has its own special set of rules for how you construct equations. You can't just do something like 2x or x squared, because 2x would be, say, if x was 1, you would get a 2, which isn't allowed in binary. There is no 2, there's only 0 and 1. So there's only some certain special operations that we can do in this type of math. One operation that you can do right away is negating a variable. This has a function associated with it called the not function. How you negate a variable is that you either put a hat over the variable, like x hat is what we would call that, or you put an apostrophe next to the variable and we would call that x prime. These are, for the most part, equivalent to each other. Certain textbooks will use either hat or prime. I prefer to use prime just because it's easier to write and I think looks a little bit cleaner. But you're free to use either one of those, and the textbook might switch off between them. This means that if x is 0, x prime is 1. It's the opposite. So negating means that if, 1 is the opposite of 0 and 0 is the opposite of 1. So that also means that if x is 1, x prime is 0. So those two things are opposite. You can have equations where you negate variables, say z is equal to x prime, so that under this equation, if x was 0, z would be 1, because z is x prime, and the opposite of x equals 0 is 1. Okay, so we can also represent this graphically, and for most of the class we're going to be representing things using both equations and circuit graphics. So how you represent this function graphically is using something called a NOT gate. In logic circuits, the NOT gate will negate a variable. So you can just draw the negation graphically. The NOT gate looks like this. You have x on the left side, or the input to the gate. Then on the output of this little triangle with a circle at the end of it, you have x prime. So basically, you can think of this as being a signal. X was a signal input to this function, not, and then you get the opposite out. So if we had a 0 input to this gate, we would get a 1 out on the other side. If we had a 1 input to this gate, we would get a 0 out on the other side. You can also, say, represent a function this way, where now, obviously, at the other end of a NOT gate, you have to get x prime. So now z is equal to x prime. So this function is z equals x prime. Another function that we deal with a lot is the OR function. The OR function uses the plus symbol. So an example equation using the OR function would be z equals x plus y. So all of these are binary variables. Z is a binary variable, x is a binary variable, y is a binary variable. The translation of this is that z equals 1 if x or y or both are equal to 1. So that function means that at least one of the two input variables has to be equal to 1, and then the output is 1. So these are the inputs, and z is the output. Z will only be 0 in this function if both x and y are 0. You can represent this graphically as well using something called an OR gate. An OR gate performs the OR function on two input variables or signals. You can also have more variables input to an OR gate, but for right now we're going to leave it at 2. So an OR gate looks like this. It's kind of a bullet shape. You have to make sure that the input is concave like that. And so we have x and y are two variables that are inputs to this function, and then the output obviously is going to be x or y, just because that's what this function does. We can represent equations this way too by saying that z is the output, which means that z has to be equal to x or y. So the function represented here is z equals x or y. The last function that I'm going to discuss right now is the AND function. The AND function uses the dot symbol, or sometimes nothing, or sometimes a multiplication. Basically, it uses the same algebraic symbols for multiplication. An example equation would be z equals x dot y, so that would be the dot right there, or nothing, which is just xy, so that's the nothing, it's just x times y, xy next to each other. The translation of this is that z is going to equal 1 only if both x and y are equal to 1. So for the OR function, it could be x equals 1 and y equals 0, or y equals 1 and x equals 0, or x equals 1 and y equals 1, gives you a 1 for z. But in this case, z is going to equal 1 only if both of them are 1. So the AND function also has a gate. The AND gate is going to perform this function on two or potentially more variables. Again, for right now, we're just sticking to two variables. The AND gate looks like this. This is the gate. The AND gate has a flat input and a round output. So the OR gate looked more like this. It had a concave input and a pointy output like that. The AND gate has, again, flat input and round output. So you're going to take two input functions, x and y, and then the output is x and y. Again, normally we would call the output a different variable, which means that z must be equivalent to xy, so the equation is z equals x times y, or z equals x and y. So that's it right now for the logic gates and the basic logic. We'll cover this in a lot more depth next week.